Yes, please start. Go ahead.
So I'm going to continue with this discussion of automorphic forms and GLN. Yesterday I talked about relational characters, idealized relational characters, introduced hacker characters, talked about the infinity type of hacker. This was an introduction to GL1. And then towards GL2, I talked about modular forms and especially talked about the space of weight K corresponds for gamma naught n with some level equals chi, which is the relational character mod n, and talked about when this thing is primitive. It's three things: eigen. It's an eigenform for all the TPs for P not dividing n. I didn't quite define the heck operator, but so that you know there's one for every prime P. Talk about reforms and normalize asking for the first Fourier coefficient to be 1. Yes.
I guess why don't we want the eigenform for P divided n?
You could ask for that. So this is sufficient for by something called strong plus P1, which I won't get into. This is sufficient.
Okay.
So Gelbart's book. So I told you this part of my talk is based on Gelbart's automorphic forms on ideal use. Some sense I'm summarizing the first 5 chapters, it's over 100 pages. He does talk about P dividing n, P not dividing n, what's the subtlety looking at everything and just looking at P not dividing. I just don't want to get into that discussion here because. So what I want to do today is, given this, I want to attach to this a cuspidal automorphic representation. Already I've seen these words appearing in other talks. And towards that, there is this idea of user. Lifting to the group. So given this F, certain object. For a large part, I don't need primitive. Maybe when I need it, I will tell you where exactly it's coming from. To this, I will attach a function. I'm going to denote this as phi for that. There are 2 levels of lifting to the group. You can either lift to the group of real points, so some function on GL2 or I'm going to directly work in the ideal situation. It's going to be a function on GL2 of the ideals. And it's going to have a whole lot of properties mirroring these various properties of F to be a cuspidal model. So, how does this lifting to the group work? GL2 by GL2 of the ideals, like anything idealic, it's a restricted product of GL2 of the various completions. Restricted with respect to for all the finite primes GL2 is LP. So this means an idealic point is a GP in GL2 QP for every P, and for almost all P for finite almost all P, GP is in GL2 Z. The gamma naught n can be thought of ideally. I'm going to denote this as K naught n. This is going to be a product of P non dividing n, GL2 Z. And for P dividing n, I'm going to use the same notation as yesterday. Like the product of all primes P to the exponent of NP, and then we say that P. Then for P dividing n, I'm going to make this gamma naught P to the MP. What do I mean by that? So gamma naught P to the M in QP. This consists of all ABCD, ABCD, and here it is P. Says that C is common to 0, or C lives in P to the MP. That power of the maximum idealism. The local analog of the Hacker congruent subgroup. So this is for all finite primes. P is this equation. So this is an open compact subgroup of 0 to of the finite elements. You will see words like level structure. This is the level structure. And this is a somewhat non-trivial exercise that G into A can be decomposed as G into Q. The principal ideas or ideas G into principal ideas and G into R plus, by which I mean positive determinant and this is there's some kind of an approximation there. So if I have an array point, G, or sometimes it's a good notational articles to pick in a bar, low bar for an array point, but I'm not going to do that. Anyway, so G here can be written as a gamma, something at infinity, and this is G infinity, and something else. So this lifting to the group is phi f an array point. You use the decomposition and you write this as I use the model form. G infinity is in G to R plus, and the f of course is a function of the upper half of it. And this is G to R plus more positive real that has over there. So it's f on G infinity acting on I times G infinity to the minus Q. That's the recipe for lifting a modular form to a function on the G of arrays. So what is J? J of immediate PCE and Z and modular function of the state function. And once you have this, you go to sit down and verify polar properties of this. This is an automorphic form. Phi f is going to be an automorphic form. And Gilbert spends many pages proving this proposition that f goes to phi f is an isomorphism from the space of weight k common order transforms with ability to side to the space of functions phi on 0 to A, satisfying a huge list of properties such that 1 phi of gamma g, you observe that this gamma here has disappeared. So it's gamma invariant, gamma and G to Q. Rho gamma G to Q, rho G to K. Very loosely speaking, a function on GA or GQ is not automorphic. Very, very loosely speaking. And then you have to keep qualifying what sort of function I'm going to look at. Phi of G K0 is, for instance, I have some derivative to phi. I take an idealization of that, evaluate of K0, and this evaluation is criteria on an ABCD is really high of D, or maybe the idealized criteria by G. Phi of the weights K shows up as if I hit this on the right by rotation matrix R theta it's cosine minus sine theta. And this is e to the minus ik theta. I want to squeeze everything into one word, so yeah, sorry.
Should the analyzed character be a part of the definition? Like, do you have to multiply that by like chi tilde?
I would like to say not.
When you flip this,
This is,
just for the left thing.
Cause like, I don't, like K naught is like trivial in this function.
Yeah, I have the same question, so
I see, yeah, okay, let me just check for a second, I think you're right. This should be. Now that's it. We have G bar.
I have another question on that
Yeah.
same topic. So here, it looks like the way you've written it, chi tilde acts on a matrix. But chi zero or k zero could be like a huge product. So I'm a little confused.
The finite part of that,
Oh, okay.
I,
So it depends. Do you want to get to something unitary, like a trivial central character or not in this process?
not necessarily. There is a little bit of hand waving going on, which is chi theta was defined on all the areas, and then I work with the finite part of that triangle. This is only the finite part. And your question of whether this is just a huge collection of matrices or is one matrix, I can think of a K naught as one matrix with each entry is an p-adic lives in the finite matrix. I can think of it as a huge collection of matrices or just one matrix with every element being p-adic. I think that answers the question. There's more. That I want to squeeze everything into one word. So I'll, each of these conditions, you just make necessary for all G, for all K naught and so on. Or there is an action of a certain operator, the Laplace Beltrami operator. If I think of this phi as a function on the real points, then it's an eigenfunction for the Laplace Beltrami operator. You don't really need to know what operator that is, but in any case, the weight of the model of function from there too. Delta is. If you're more familiar with differential equations, or if this is the way as a group theorist, it's easy to think of the Casimir element. In the center of the enveloping algebra of SL2, there is a certain special element called the Casimir. So it's the action of the Casimir. There's a central character. Phi of ZG is phi of GZ, which is the idealization on Z by G. This is for all Z in the center. This is just yields all the scalars. What is? There is some growth property. Phi is slowly increasing. Which again, I don't want to get into the meaning of this. Kind of like what showed up in other stuff. The Vedic functions had some kind of asymptotics and some growth, somewhat along those lines. So along the torus, it's bounded by some power of the elements, absolute value of the elements in torus. And lastly, so this needs talking about, which I won't get into, phi sub. So capitality is this integral. Next to 1 G dg dx 0 for all for G almost everywhere. What we are staring at is essentially goes into what is the definition of an automorphic form. Slightly relaxed. With some conditions could be possibly slightly relaxed. In my original preparation, I had planned on doing this lifting two levels, one to the level of real groups and then to the array points. So let me just put down where is my decomposition? This similar to this decomposition. This is the one sentence apology. This is another exercise. K infinity. I'm going to change my K infinity later on, but this is right now. Go to the maximum compact distinction. I hope I got this right, or up to minor tweaking this side and that side. This is correct. So what's happening? You start with for modular forms of functions on the upper half plane, which is Fn2 mod SO2, with some equivariant with respect to gamma. Then you tweak it, you do this, and what you do is now it is invariant under gamma and equivariant with respect to the maximum compact. Equivariance is captured here. Okay. So initially it was K invariant, gamma equivariant, and then you tweak it, thus, and make it gamma invariant and K invariant. So these are really functions on Fn2R, so G mod gammas. So another you can develop automorphic forms, Harishchandra style, working with functions on GL2R or GR for any real directed group G, and invariant under some discrete function gamma. Okay. So definition, automorphic form. On GL2 or Q, then the function phi on G8. So G is the group, algebraic group GL2 over Q, and in your mind you can start making this for GLN over a number field. And if you want to work with a Q group, you can use this artifice of the way restriction of scalars. You restrict from JLNF from F to Q, produced by yourself the Q. Such that similar problems. So phi is invariant under that translation by gamma for all gamma and GQ, for all G and GA. An automorphic form is a function, an automorphic form that is given here with central character omega. So omega is identity character F of the number field F or Q, whatever is the context, and so that this has a central character. G for all Z and ZA. So this equivariance under SO2 there is vegan, and you ask this phi to be this K finite. So what is K finiteness? I have a function, you call it K finite if the K or the span of the K orbit, the finite dimensional space. If this function lives in a finite dimensional K stable subspace. K is something at infinity and your level structure K. Fourth, as a function of the real points, we want phi restricted as a function of GL2R or GLN of F tilde R. This, I want this to be the right center of the enveloping algebra of the Lie algebra. Or maybe here, let me just say, make this K finite and include here Z finite. People usually say Z finite and K finite.
Say again, what K finite means.
It lives in a finite dimensional subspace of some ambient function space, which is stable under K.
For three, you can just write it smooth for three, and smooth means like K finite for finite, and
Yes.
then you need smooth to differentiate for the fourth condition. So you
Yes,
put
yes.
smooth is the third condition.
I would certainly need to put it smooth and Z finite. And this is really smooth in the p-adic sense of in the sense of Navier-Stokes, that you're looking at locally constant functions on a totally disconnected group GAF. And finally, some growth conditions. Moving increasing. This is roughly like phi on a, let's say on an AA inverse. Anyway, on the center, I know what's happening. So on the rest of the torus, this is kind of bounded by some number. And furthermore, if further, I have a condition like this. So almost everywhere. G, that n is the uniform radical of any parabolic subgroup. So as I go along, I'm kind of drawing more from the language of algebraic groups, parabolic and proper parabolic. All the integrals should be zero, and all of this. This condition, by the way, because of hitting it on the right here by this G, it's taking care of vanishing at a cusp, at every cusp. You remember from model forms, we talked about working with one cusp, and then for any other cusp, we move it by an element of S2, and then you write down the Fourier expansion, the first coefficient to 0, 0 coefficient to 0. That's taken care of by that G. Okay. I'm going to let A first DQ on GA with the central character omega denote this space of hospital automorphic forms on G with central character. And I'm going to denote L2 cusp for all this to be this space of hospital automorphic forms intersect with the space of L2 functions on GM or GQ. From that, you might catch me about unitary or not, and there's a little bit of something. It's part of the game. And in fact, Langland says somewhere that you simply have to keep track of the bewildering array of function spaces in the game automorphic form. And you're seeing two such spaces here on the board. Even if this one I haven't really defined it, but some issue with some measure. Okay, so where were we in our business of lifting to the group? You have this function phi f, which lives here with all these properties. So for the group GL2, it lives in this space, and so back to my F being F3, comma not N I. Let me just say primitive. With this, we attach the representation phi set F, which is the GK representation or sub-representation of a cusp. 0 to Q, 1 0 to A. The central character, the idealization of the nebulous sky, generated by its
The way you define it, because it's a module of the global tech rather than.
yeah, so that's another big discussion one needs to get into. At this moment, all these spaces are acted upon on the right by GA, but really one should be working with GA, we should work with GAF and some kind of infinity about it.
No, that's the whole point. G doesn't act to the right.
It's just GA.
At this moment, GA is okay. This
So you have this K infinity is a fixed thing, right?
I need a global head GAF cross some kind of head algebra that you build. Yeah,
Also, I thought the L2 space is like much bigger than this space you've defined, so it couldn't possibly be like section.
this space is large because
Like this space you define, it like embeds into the L2. Space.
Not all forms are L2.
here I only ask for slowly increasing. There's no reason for this to be like. They're just different spaces. I can take something which is common to both of them. This, all this together with some kind of square root.
I guess your definition.
John, you were commenting about this. We shouldn't really get in too much into what is the automorphic form. Okay, it becomes a problem. Right? It is part of the painfulness of the subject. You somehow recognize it when you see an automorphic form, but you don't really get into too much. There are all these details to be ironed out, and it's impossible to do that in a talk like this. Lyman also says somewhere, let me not worry about what an automorphic form, but let's just start talking. I'm going to. Yeah, no, you guys are getting, yeah, whatever, there's a huge discussion which needs to go into this, but this is just bird's eye view. And now there is I have to assert that this in fact is a irreducible representation, which comes out of this primitivity. So there's a bunch of theorems, none of them trivial. I'll just state some facts. The first is, well, this L2 cuspidal GM or GQ, some central character omega. This is very general. So this breaks up at the direct sum over whatever shows up. I guess you know that phi, and even this appears with finite multiples. This is very general, and it's just functional analysis. Goes back to the Gelfand school, Gelfand created Shapiro, and Gelfand Gray created Shapiro. That book, I think, has to be a position like that. So anything that appears here, these are the hospital automorphic representations. By definition. If I have one such I is hospital automorphic representation, this is the Daniel Flack's thesis. Maybe some part, something can be relaxed. In any case, so this is after all the group is some kind of restricted tensor product. I think about a restricted product. So you should expect the representation is a restricted tensor product of local representation. So phi p is an irreducible admissible representation, which we saw in our box. At this moment, p could be good. For GL, so actually these two, still I'm working, very generally. Now if I specialize to,
GFQP.
sorry,
You put GFQP.
yeah, DFP is better because it's still very general. If I take G to be GLN, for a number field, all these multiplicities are one. Or maybe I should say less than or equal to one. Whatever appears, if it appears in multiple field one. So this is called one. And this uses Vedic models, which you saw this morning. The global version of what you saw locally this morning. And this representation, so F is now weight K, level N, character chi, primitive. We need primitive at this stage, then it's pi is an irreducible hospital automorphic.
If it's a hospital function and it's slowly increasing, then it's automatically decreasing. So
Yes.
hospital function automatically.
Yeah, but here I think there was, it was not, need not even be measurable.
But you are assuming it's smooth at infinity. So it's
So it has to get taken care of.
so you have to get a bit.
It has to be analytic, and since it's locally constant, it will be adequate variables, it's, yeah, I suppose it's also measurable. Agree? I agree.
So you don't need to take a second, it's just a closure.
Okay, fine. Agree. So, still talking about the dictionary between model forms and customer representations, I want to see these details, the weight and the level, the character shows up as a central character. I want to talk a little more about the weight and the level. And for this, I need some local ingredients, some statement about the local representation. So, let me just introduce the discrete series representations. Some local ingredients. I have an Archimedean local ingredient and a p-adic local ingredient. So first is something about GL2R. Suppose I'm going to deliberately write this in a slightly more general language, which will be useful when I get into cohomology. So suppose I have mu is a pair of integers. Say A is greater than or equal to B. This is a dominant integral weight for GL2. I'm going to let n mu stand for the A minus B symmetric power of the standard representation. Tensor determinant B. This is the finite dimensional irreducible representation of GL2. Actually, all this was algebraic. You can see how it's going. What Nader was doing theoretically with induction, we can work with wave groups. If I deduce from the Borel of GL2 to GL2R of the character chi A twisted by R, chi B twisted by minus R on the torus. So chi A is the character which sends C to T to the A, and chi A twisted by R is the character which sends C to T to the A and its absolute value. And likewise for chi b to the minus, this is the minus half. This induced representation is not irreducible. And the way this is set up, it has this finite dimensional representation as quotient. And by definition, whatever is the sub, I'm going to denote this as dV. Defining dV. I'm asserting that this induced representation is not irreducible, it decomposes, and it in fact decomposes the irreducible quotient and irreducible sub. The way it is set up, the quotient is a finite dimensional representation. So this short exact sequence does not split, and this is. We will get into homology in a minute. If I take K, let me just for simplicity, more of my convenience at the moment, otherwise I'll worry about some these things. The half, if K is even, if I take mu to be it's K minus 2 times half the sum of positive roots for GL2, that's this page, K minus 2 by 2 minus K minus 2 by 2. Then this mu is the K minus 1 dimensional. And this d mu is I'm going to know this is dk minus 1. This discrete series inputs. GL2R technically doesn't have discrete series. SL2R has, PGL2R has, but not quite GL2. So you're familiar with what I just said. You understand why I put the code, but otherwise it's just words. I denote this dk minus 1. Discrete series representation. This is what shows up as the representation of infinity. If I attach back. Representation of infinity. And at a finite place, you want to see the level, and here there's a very beautiful theorem. Just want to show you this theorem. There is a beautiful QT, I can work with p-adic. There's a beautiful theorem which you have. This is the local theory of eigenvarieties. The new forms business for modular forms has a local aspect, and this is. So if I take phi v to be an irreducible admissible representation of GL2 F, F is now p-adic, you can take F to GP with central character. Take omega. So define P naught P to the M will be, well, I guess I already defined this. I don't need to write this on. Sorry. So I'm going to denote Vm to be the set of all vectors V in V on which the hypercongruent subgroup acts via this character omega. All k in this hypercongruent subgroup of level p to the n. So V0, if n is 0, then we just take this to the full GL2O. V0 is V1, it's in the so it's conceivable that they're all zeros. Okay, and if I denote C pi to be the minimum, the least m for which Vm is not 0. There is such a C, suppose that it is not 0 at some stage, and at that stage, then the dimension of the space of if there is no central character is like this vector, that dimension is in fact 1. Actually, Casimir is something little more stronger. The dimension of the n is n minus c5. That's one. This dimension of space of essentially fixed vectors grows linearly. The c5 is called the conductor exponent. Then we define after the theorem, we define p to the c5 to be the conductor. So there's this very beautiful local theorem. We just need some very pleasant representation theory of the p-adic field. Whatever you need is already there in Raghuram. Casimir even says something like these are easy pickings from Raghuram. And then back to my global back. If I take F to be this weight case rather than primitive, then this n, or if I take the ideal generated by n, this is the product for all the finite primes p to the conductor of the local representation. I guess it's a different working pattern primes. So the level is seen via conductors purely representation theoretic. Then asking for the first level, the least m for which there is a fixed relationship. That's fixed, if not efficient. So I see the weight of the modular form in terms of the representation at infinity. I see the level of the modular form in terms of the finite part of the representation as the conductor. The divergence becomes the central character. So this gives you the dictionary I stated last time.
One is not square integral in one central. In the Archimedean case.
Yes.
It is or it is not.
Oh, it is. It is. So here, the central character is in fact for dk minus 1, the central character is trivial on positive reals. So it really goes down basically to PGL2. So where there is discrete series, it is discrete series in the terms of values. It appears discretely in that L2. So now I'm going to change tracks. But this short exact sequence, I'm going to leave it on the board. I'll just say how this is going to come. Real time reorganize my thoughts. A short exact sequence gives you a class in X1, in a suitable X1 between these two modules. That X1, after rethinking, is a cohomology class in degree 1. Okay, so that's the relation where cohomology kind of comes into play. Now I'm going to set up, put myself in the right context to talk about cohomology, for which my space, I want to talk about locally symmetric spaces. This is upper half plane mod gamma. Let me set this up. I'm going to take G to Q, or I could take G to be the decision of scalars from some number of G and then whatever. I'm going to work with GL2 over Q. Everything I say really can be, I can do it here, or in fact, even more generally with the connected production group. GR is GL2R. Here is GR into the product of GL and R's. Depending upon the GLN of F tensor R. C infinity is going to be my maximum compact subgroup of GR. So for GL2, this is the maximum compact of GL2R is 4-2. So in this bigger example, this is a product of ONs for the real places, and for the complex places, the unity to even standard unity. I'm going to take Z to be the center of B. So this is just scalars and GL1. Here is really the restriction of scalars from actually Q of the center of GLM. It is scalars of GLM. S, I'm going to denote as for my maximal central split points. So for GL2, this S is Z itself. It is the scalar GL1. Here there is a in the bigger example, this S that's going to be a copy of GL1. It sort of sits diagonally in this center. Or let me get my the maximal compact K infinity. That is not quite the maximal compact. The maximal compact thickened by a little bit of the center. The real points of the maximal center split torus. So this FR equals this R cross, which sits diagonally in this product of the GL and R's. As scalars. My level structure KF is going to be an open compact finite hills GAF. This is the analog of my K0 N and SGKF is this double poset space GQ GA mod GQ mod K infinity circle. K infinity circle is the connected component of the identity. This is an idyllic version of the locally symmetric space. There's a purely differential geometric way of talking about a symmetric space, locally symmetric space. And this is up to a little bit of fudging. It's the locally symmetric space. A little bit of fudging is, let me just explain that in a minute. So this is, what does this look like? Via an example, the sort of decomposition because here, right in the beginning, GA is GQ, GL2R plus, and K0 N. So, using such a decomposition, one can realize working purely with the real points, there will be some discrete subgroups, gamma i's, and the finite disjoint union of we have to even and technically what one needs to do is if necessary shrink KF a little bit such that all the gamma i's are perfect. If I take the upper half plane mod SL to Z, SL to Z has these two little points where there's a little bit of pinching when I do upper half plane mod SL to Z. So if I go instead of SL to Z, if I go like gamma naught N, or N is at least 2 or 3 or something, maybe gamma 1, 2 or gamma 1, 3, then there's no elements of torsion. So that takes care that the map, so the upper half plane to upper half plane mod gamma will be a covering map. That's what I would mean. So that's what this takes. Then it is an honest equivalence to this space. Next ingredient to talk about homology is I need some shields on the locally symmetric space. This shape comes from this kind of a representation. If I take any finite dimensional representation, so if I take mu to be, let me use the notation from small something like this, the highest weight for JLN, or if I want to work with this example of GLM or any number field, I would take mu to be a weight of the torus there, so I would expect from F to Q of the diagonal torus CL over F. And then we say if I just base change everything to some splitting field, F Q E, this is some splitting. You can take any normal closure of F or any field containing that. And ask for this to be dominant. If I'm working with B is GL2 or Q, and this mu is just a pair of integers A, B is A. Maybe I just in the interest of time work with this easy, very concrete example. And then mu is this absolutely irreducible finite dimensional representation of the group G cross E. So here, again, this concrete example, this is I already put it down there. A minus Bx symmetric of the standard representation Q2 listed by the determinant. Purely algebraic and it's absolutely irreducible after any ratio. This gives me a sheaf. Mu filter is a sheaf on the locally symmetric space. And let me show you the construction of the sheaf. So what's a sheaf? For every open set, I need to tell you what the sections of that open set are. So mu filter on any open set. So here is my SGKF. GA or GQ mod K infinity KF. So consider this vibration GA mod K infinity KF. Dividing by GQ is this vibration. So take any open set, lift it up, call this maps, call this pi. So the sections over an open set V are all functions from pi inverse V to the representation space mu, so that say what kind of function that will be. That's is a finite variable smooth and the p-adic variable. So just use the word smooth. Take care of both kinds of smoothness, such that no, I'm going to go back to locally constant because I want to do this purely algebraically. Such that S of any I can pi inverse V is GQ stable by definition. So if I move it on the left by anything in GQ, then it will act if I call this rho mu and mu as rho mu is the representation on the representation space mu, rho mu gamma X. So I just gave you a recipe for sections over an open set. And now you have to sit down and got to check that this is in fact size. Check. There is a not entirely trivial exercise, but we can look this up in Harder's or my book with Harder or Harder's inventionist paper from the 80s. That the sheaf for the sheaf to be non-zero, even if the representation space is something non-trivial, it's possible because of some reason that the sheaf could be zero. For the sheaf to be non-zero, it is necessary for the central character of this representation mu to have the infinity type. And this is the reason I introduced the infinity type yesterday. Infinity type of an algebraic hypertype.
Because you put very little center, probably here, that's not necessary. Right? Because you put a very little center here, you just put the center of Q basically, so.
Yeah, there is, but I'm still getting by some little bit of center. So you have to worry about the units in that part of the units in that part of the center.
There's no much units because you just put Q. So I think that maybe the only reason I was going to ask you why you put so little center there. So it's maybe not to have this condition precisely. If you put the whole center, then you have the unit condition, but if you put that little center, it's just like plus or minus one kind of thing.
I have to think a little more. First reason to put a little bit of center here, if not, the space will have infinite volume. So if I didn't kill by anything in the center, then it becomes like the upper half plane. Mods on the street are okay, but times align, and that makes it infinite volume, the positive real kind. So I want to kill that. So that's the first reason of killing something in the center. Then this comment, so Nardal is saying, if in K infinity here at second point, this then this condition is really maybe I just have to reflect a little. And so once you have a space and a sheet on it, the basic object of interest in the subject of homology of arithmetic groups is the sheet homology group. And if I were to do this generally, have a steady field E, then everything, this would be an E vector space. This would be all happening over some field. And it's good to do this over some arbitrary field and then necessary base stage product. So this is a sheet. Why is the subject even called homology of arithmetic groups? Comes from here. So this space, the connected components are all like this. So if I were to just work with one of those connected components, if I look at the homology of VR mod A mod gamma with coefficients in some sheet and mu E tilde, and if there is no pinching, no torsion, then this is in fact isomorphic with the group homology of gamma, thinking of this representation space as a gamma module. So this is group homology. Just justifying that the name of the subject is homology of arithmetic groups. So, run out of time. There was two more things to do, which I'm going to do next time. But let me just state something where this gets related to this short exact sequence. That needs some final explanation, which I'll start next time. But let me just put down some things since John, you said you might be Eichler Fumura. There is a famous isomorphism called the Eichler Fumura isomorphism, which takes the shape that the space of weight K corresponds to gamma naught n. Let me in fact not do this with central characters because that's an additional baggage. Let me just go to gamma 1 and this. There's an isomorphism of this. It's called the isomorphism, mapping into H1 of the locally symmetric space for GL2 over Q. And the gamma 1n has its corresponding adelic level factor K1n. And the weight K, let me assume A P1 for convenience, and I take this mu to be K minus 2 by 2 minus K minus 2 by 2. Corresponding, like if I call this mu sub K, M mu K tilde. For this to be an isomorphism, it actually goes inside this H1 and something called cuspidal part of H1. Or in Shimura's terminology, this SK gamma gets mapped into H1, what he called parabolic cohomology. And with a vector space VK, which is a representation space here. So there is such an isomorphism. I will talk a little more next time how this isomorphism arises. Maybe not so much, but really focusing on the H1 and the H1 cuspidal. And why H1? The H1 nest, the 1 degree nest is related to which part of that. So that relation I want to kind of bring it out. That's the easiest way to introduce the compound.
So maybe like reals on the right, it's complex on the left, or
Yeah, once again,
plus or minus thing. Plus or minus.
and really there are two isomorphisms I have to look at.
I just hate the plus minus sign.
Yeah, so observe that I'm dividing by the connected component here. And because of this, dividing by the connected component, on all of these guys, there's an action of K infinity mod K infinity circle. Which here, K infinity mod K infinity circle is O2 mod SO2. So there's an action of this Z mod 2. And we can decompose it as into eigenspaces for this Z mod 2 action. For each one of the eigenspaces, there's one copy of the Z mod 2. Theta depends on the group of connected components here. You can do things with modular form, say it's Snellen transform, there's an N function. You can work purely homologically. There are maps coming, say, from Poincare radiality and so on here. And an interplay of these two gives rise to the theory of special values of the functions. So that's really where I headed towards. So I'm going to pick it up from here.
So I guess like perhaps roughly speaking, like for some cusp form on the left, what you're doing is you're associating it to some like representation on like a big group ring gamma. Just by
To a cut form, what one is really associating is a differential form in degree 1 on the space, but it's not just scalar value differential form. The differential form takes values in this representation. So that's a good way to organize it.
So, okay, so it's something like that that used the short exact sequence. So
No, it's really as you said. I mean, it's really what he said. It's
The different, if you take a weights 2 cusp form, F, and I do F of Z dz, then this becomes a differential form on degree 1 on H1 down. So that's somehow make a peace with that. And then this is a slightly fancier version of that. It's because it's not a complex, this is not scalars, but it's some vector bundle on the space. So it's a differential form taking values in this bundle. More is coming up about this, really this, and what you can do with these homology groups and L functions. That's okay.
Oh, like in the case of weight 2 forms though, or like, isn't, I mean, this is just like the Hodge decomposition, but like, or like a piece of the Hodge decomposition. So is the content, I guess my question is this like very clear in K equals 2, or is it like the content that like, something like Hecke covariance?
No, Hecke equivariance needs to be full. So
Or I'm saying like, is that like the content of the, like I'm saying in weight 2, like weight 2 forms are just like differential forms.
weight 2 forms, yes, are differential forms. And weight
So
higher, there's not so much of a difference between weight 2 and higher weight, as long as you carry through this baggage.
Yeah.
But it is an important part of this, the proof, in fact, of this isomorphism, that this is in fact Hecke equivariant.
it's okay. It's yes and no. Like you got the right idea, and as Raghuram said, the idea is like, but coach decomposition, that's like for proper schemes, right? And this thing is open, so there is a little bit of subtlety, I mean.
Well, like, shouldn't this be like? Like, shouldn't, like, for the, at least in the case of the modular curve, shouldn't, like, just, this should just be compactly supported in
No,
homology, and so then.
You prove that this
It's
parabolic homology is isomorphic to the cohomology of the property, and then you have a coach decomposition. But I'm just saying, it's not like exactly coach decomposition, it's like there's some steps. Like it's not like exactly the coach decomposition for a proper.
I'm going to put a shriek there and denote this H1 shriek to be the image of H1 compact supports inside global H1. To kind of relate to what you just said. And this, the Shimura didn't write it in this, writing it as H1 shriek. He actually, Shimura style, very concretely, basically talks about this, but working algebraically inside the group gamma, you kind of cut out this and cut out that, and then I. But this is the sheet theoretic way of talking about bringing in inner. This is called inner comma.
What is right? It's a formal or it's.
This one?
Yeah, or,
This one is basically formal. You have to realize, so what is sheet formology? You take, so you fix a space, you look at the category of sheets, they are available, and you look at global sections, and that's left exact functor, and then you can complete it. So that's how you get sheet formology. That's the definition, but that's what we use, how we compute it. So for computing this, you have to take some resolution of the sheet, and then you apply global sections, you raise the zero term, and then take. If you go through that, then you will realize that the complex which computes this sheet cohomology, after reinterpreting, is literally the complex which computes the group cohomology. So that's basically what it comes from.
I mean, what are the global sections of FP chaos?
Well, it's all functions on right here. It's all functions on dA mod. So what is this space?
Well, you know, that the global sections for MU utility, but like, is there
Maybe you could structure sheet.
yeah.
No, I don't think I understood your question. Asking it.
Is there like some sort of structure sheet on SGKF?
It's a manifold, so there is no.
no function sheet. So here, this is like a cohomology. So you just need a linear functional on the cycles, and you do this by integrating your differential form. It's very down to earth. It's like it's meticohomology. There's no like structural sheaves or anything. It's just real orbifolds, whatever it is.
At the moment, it's just a topological space.
You run to get constant coefficients, you take the constant sheet. Let's make it work.
Yeah.
Yes.
So if you take like H mod gamma, what will the sheet look like in that simple case?
You have to go through this construction. So there's another way to talk about this. Since you asked about H1, now I'm going to display it here. You go to the upper half plane, and you got this representation space mu. So just take the product of these two. Gamma acts on upper half plane. It acts on the vector space by the representation. So there's a diagonal action of gamma on this product. But before I talk about that, from this product, I can simply project to the first factor. Now I bring in the action. There's a diagonal action of gamma on this. And so the projection to the first factor induces this map. This is the vector burden on my space. Okay, and then I'm looking at sections, shape of sections of this. So I have an open set here. And then from this product, I can project to the second, and then you kind of go like this. That will give you another way to organize it.
So mu is just it
M-
will just be this.
It's just
There is it doesn't become something we know in case of H mark.
It becomes, whose talk, I think maybe was it your talk, someone talked about homogeneous polynomials of, was it you? And I don't.
Aladdin, I mean, Aladdin talked about it, but it'll come up in my talk.
Okay, so if you take this for weight, for the related model forms, let me just work with K even. I do this, this is A, that's B. A minus B is K minus two. Ah, good. So symmetric K minus two of, so sim K minus two of the standard vector space. This is the so this is dimension K minus one. So this is K minus 2 degree. That's one homogeneous polynomials in two variables x and y. So it's spanned by x to the K minus 2, x to the K minus 3, y, blah, 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 x, y to the K minus 2. There's so the GL2 people will often write like this. If you want to work with automorphic forms and higher groups, you have to work with the language of iceberg.
I just wanted to make a follow-up remark. Is that, I mean, of course, there is a relation to course decomposition and safety variant also because this kind of theorems is tutorial. So, but for the rest of the week, it's almost better if you forget what's an algebraic variety and the Raghuram cohomology and things like this because first of all, there's no such things for GLN. It's specificity of GL2. And we will only use somehow the topological structure for the totally disconnected constructions that we'll do. It almost helps to forget the specificities of GL2. For those who know much.
Yeah.
Very fun. Here's another. I'm gonna compute some of the electric homology here. Draw a lecture and I'll make them really feel like this is gonna be.
Yeah. So
Like I'm gonna take open your function on chains. I didn't have you. I think all my normalizations are fine and they're not complaints about them. I am. Somehow I don't really, you have this twist by that E. So in your normalization for weight K form, there is a twist, but it's permanent. And somehow, I'm not gonna put that twist there. And
On one side, you have H1 of like X1 of N. C